Welcome to Lecture 7A. There are two lectures constituting Lecture 7. In 7A, we'll discuss the tangential plane and linear approximation to curved surfaces. And so this is just more of a prologue to more detailed treatment in terms of the mathematics in Section 7B. So this material is covered more or less in Section 15.6 of the text. There are some additions, and we'll mention that on the next slide as well. So the objectives are to give motivation to the importance of approximating multivariable functions about a given position, and also develop the confidence in visualizing and sketching a tangential plane. The concepts and visualization skills we're looking at are the understanding the application context of tangential planes. There are many sort of situations in which tangential planes are used, but they take on a different meaning, and yet mathematically they're the same. And secondly is to get some practice in terms of visualizing tangential planes and also sketching them. Just as a brief reminder, we had discussed tangential planes when we introduced multivariable differentiability in Lecture 4B. Here we will basically look at things in more detail. All right, so this is the outline, but I just want to make note at the bottom that items 1 and 2 are not in the textbook. So this is going to be new to you. Item 2, note 2 is item 1A is discussed in assignment 1, but you're not responsible for this material. It goes into much more detail with some examples. So if you ever have the time or in the future, if you need to know more about it, there's more than enough material there to digest. And note 3 is item 1C. This is discussed in assignment 2, and we'll have more to say about that in the next lecture. All right, so we'll move on to the next slide then. So the motivation to approximating multivariable functions. So I've marked this in green, and the next slide will also be marked in green. These are the topics that we'll be discussing in this lecture. So the first thing is the notion of a tangential plane, but specifically related to geometry. In other words, literally in the real world. And you would ask yourself, well, where would this play a role? Well, particularly in kinematics. And that's basically what we're covering in this lecture. So kinematics would be, for example, if you have a ball and you let it roll down a hill, and you keep the problem as simple as possible, neglecting friction and things of that nature, and you want to know in what direction will the ball go down the hill, and what will its speed be, and its acceleration, and its position as a function of time. And so that's basically the type of problem that one could solve using tangential planes. So let's just go through each point in turn. Near a given point on a curved surface defined by z equals f as a function of xy, the surface can be assumed to be planar. So if you just look at a tiny region at a given point on the surface and walk in all directions, it will be very, very, very flat. And then if you get further out, you'll realize that there is actually some curvature. The plane which just touches this curved surface at the given point on the curved surface is referred to as the tangent plane. All right, so effectively, if you make the area very small, then that being a flat surface, that will actually mate very nicely with the tangent plane. Third point, the motion of an object on a curved surface can be decomposed into a component of motion normal to the plane and two orthogonal components of motion tangential to the plane at any given point on the surface. And this material is dealt with in more detail in reading assignment 1. And again, as I mentioned, you're not responsible for it. So if you look at the diagram below, I think that perhaps will give you a little understanding of what's happening. So at this point, we can essentially say there's a normal component, and we know that's going to be a gradient vector. We've already discussed that before. But you have also a tangent component, which is tangent to the motion, tangent to the direction of the motion. Now, clearly, at every given point on the surface, the direction constantly changes. That's okay, but we still define as being tangent to the motion. But we also need one additional coordinate, which would be orthogonal to this vector, so that it also lies on the same tangential plane. And we can obtain that by just taking the cross product between the normal vector and the tangential vector and produce a third vector, which is n cross t. So when we derive the equations of motion, we'll have an equation of motion for this direction. We have an equation of motion for this direction, and equation of motion direction for this one at any given point on the surface. Typically, the equations will be nonlinear, but they can be solved as discussed in reading assignment 1. Again, just to reiterate, you're not responsible for the material. This is just to give you some motivation as to how we would use it and what context we would use it. Okay, so next. All right, the second thing is time-independent physical models. So this normally we call sensitivity analysis, and again, it will be discussed in this lecture. So let me just give you an example. A multivariable function can describe the physical relationships between output variables and input variables. So for example, the cost is a function of losses and efficiency. So for instance, if I buy a power supply, I know that it has a certain amount of efficiency, and I know that there are a certain amount of losses that are generated within the power supply, and those losses create heat. And I want to understand what would be the cost of a power supply when it's purchased, and how does it depend on the losses and the efficiency. All right, so this is just one example. Second point is the variations of the output variable for small perturbations, which are small changes in the input variables, and the input variables in this case being efficiency and losses, is linear, okay, and is also referred to as sensitivity analysis. So what we're trying to do is to say, if we basically make small changes in the input variables at a given point, in other words, let's say the losses are 10 watts and the efficiency 80%. And what you're asking yourself is, how would the cost change if instead of having 10 watts, I go to 10.1 watts and the efficiency goes slightly up, say maybe 0.1%. So is it super sensitive to small changes? That's called sensitivity analysis. Thirdly, because it's basically a perturbation analysis, these are going to be linear equations. The system of linear equations can be converted into non-dimensional units in order to compress the range of the numbers. Now, this is referred to as per unit analysis, and I'll demonstrate on the graph below. So per unit basically allows us to scale everything so the number range is very, very sort of compressed. And from a numerical standpoint, and even from the point of view of understanding what are the main factors that affect the nature of the function, are easier to understand in a per unit basis. Per unit, of course, has no dimensions. All right, so in the figure below, which I'll describe shortly, the cost and the losses have been normalized, and therefore they have no units. So essentially what I'm saying is, take the cost and divide it by some nominal cost. The ratio of those two has no units, and that's what I'll be graphing. Similarly with the losses, I take the losses and divide it by some base loss. That's basically now normalized, and the losses now have no units. Secondly, efficiency has no units, but you could still normalize it because efficiency is normally between 0 and 100%, but you can scale that from 0 to 1 if you want, just dividing through by 100. So we typically use 0 to 1 in terms of the per unit analysis, post-normalization. The normalization comes from the loss, for the loss and the cost are choices made by the user. You decide what normalization constants you want to use to make the problem as simple as possible, or in many cases, the choices are very much practically based. So the picture in the lower left-hand corner, this shows basically two operating points. And so you've got losses in this direction, efficiency in this direction, and these are on a per unit basis, so no units. So what we're interested in knowing at this point here, if we move a little bit in all directions here, what impact will that have on cost? Well, if you take this point and map it up to the actual functional value, which would be Z, this will be per unit cost, you can essentially see that this is how the costs will vary as you vary the efficiency and the losses. Move to a different operating point and you'll find it might be much more sensitive. Small changes might lead to dramatic changes in the cost. So this is just a sort of a legend showing you that the black circle on the XY plane is the zone in which input variables are varied. The black circles on the surface is the range of values as a function of range of input variables. Black dots on the XY plane are the operating points. The black dots on the surface are the output variable at a given operating point. So that means we're just going straight up to this point right on the surface. All right, in the next lecture, we'll look at the third item, which is time-dependent physical models, also called small signal modeling, will be discussed in lecture 8. And so if you look at the diagram below, I've got this box. I've got these input variables, m possible, as many as you need. I've got output variables, y1, y2 to yk. And in this box, I have what we call state variables. We'll be discussing next lecture and to some extent in this lecture. These are state variables that could be, for instance, if this was a circuit, it'd be the current through an inductor, could be the voltage across a capacitor. Typically, these state variables are associated with storage components, energy storage components when we're dealing with a circuit environment. If we're dealing with mechanical circuits, it would be inertia. In other words, the moment of inertia. So, I mean, these are things we'll discuss in more detail. So the state variables basically are tied to something quite physical, and there might be n state variables. Anyway, this is very generic. So let's go here then. So the output variables, y1 through yk, will evolve with time in response to small signal variations in the input variables. Right, the input variables being u1 to um, and the state variables are x1 to xn at a given operating point. So what do we mean by operating point? What we're basically saying is we're going to run the system at a static point so that u1's held constant all the way up to um. That means yn, y2 up to yk will take on constant values. And so then what we'd like to do is to figure out that if we make small changes to u1 through um, how will that impact changes occurring at y1 through yk? That's basically what we mean. So operating point, you might say, is basically a DC value at which the system is currently operating. You want to change the operating point, and you would change the DC values at which the various input variables are operating. Second, dynamics of the system is governed by coupled or decoupled differential equations involving the state variables x1n and the input variables u1 through um. We'll be discussing this on the slides to follow. So at this point, the difference between coupled and decoupled is easier to discuss in the slide to follow. Third is that dynamic equations can be converted into a per unit non-dimensional form in order to compress the number range, simplify post-processing analysis, or numerically precondition the equations. So this is similar to what we did when we dealt with sensitivity analysis. It just makes life a lot easier, and it gives you a better understanding of how the differential equations depend on specific constant values in the system. All right, so here now are some of the examples illustrating multivariable function to be approximated at a given operating point. So we'll take the three cases that we mentioned before. The first one on the top left will be geometric. The one on the right at the top, more to do with a physical application where sensitivity analysis plays a role, and everything below it is small signal modeling. So let's look at the top one. Here I've basically given you an equation of a sphere of radius 1, and I've given it to you in implicit form. And the typical problem might be to determine the tangential plane at a given point on the sphere. Okay, so that's basically just a statement in terms of what we might be interested in doing. Let's come over here. Here's an example of a physical problem. You're given that the cost is a function of the mass and the footprint, right? Footprint meaning the surface area. So the bigger the surface area, it's more real estate, you expect the cost to be higher. The more heavier the object, right, more costly, because to transport this object is probably going to be more costly as well. So it just gives you some idea. And the typical question here might be, determine the cost sensitivity as a function of small changes in mass and footprint about a nominal value of mass and footprint. So that's basically a sort of a statement in terms of what we might be interested in. The thirdly is with small signal analysis. We basically have two sets of equations to consider: the state space equations that you see here and the output equations that you see here. Now, what is a state space equation? A state space equation will typically have a differential equation, right, or just a derivative term on the left side, And on the other side will be everything involving state variables and input variables. Here's the second one. So every state space equation will have a unique state variable, as you see, x1 and x2, and everything on the right will be involving the input variables and the state variables. If we're dealing with a coupled set of differential equations, means that the terms on the right will involve all state variables, or most of them. So you'll notice here there's an x2 and there's x1. Similar here, x1, x2. If we talk about decoupled differential equations, then this differential equation will only be a function of the state variable x1, and this will be only a function of state variable x2. The output equations basically will be just some expression in terms of state variables and input variables. And so the next thing would be to consider what's the difference between a nonlinear differential equation and a linear differential equation. Well, in this case, basically, this is nonlinear. Why? Because you'll notice the state variable on this side is squared. All right, and if you look at the output equation, it's a nonlinear equation because one of the input variables, u2, is to the fourth power. If these had all been linear in the state variables and input variables, then we'd be talking about linear differential equations. Right, so the state variables will be the ones on the left that you see here, x1, x2. Input variables in this case are u1, u2, and output variables are y1, y2. Now, in discussing these types of problems, we always need to also know what is the operating point about which small signal inputs changes are going to take place. And so we give special labels for the operating point. We basically would say that under conditions of static operation, operating point, that means there's no change taking place in anything. The input variable is constant, the state variable is constant, output will be constant. Well, if it's constant, mean that the time derivative must be 0 for both state variable x1 and x2. So this is the condition that you see over here on the right. So under those conditions, you have this equation and this equation, and they have to be solved simultaneously. In this case, it will be nonlinear coupled equations. All right, so if that's the case, then only thing that's given would be what is u1 here, what is u2? These are static values, those will be given. But x1 and x2 will not be given. In fact, you have to solve for x1 and 2 by solving these two equations. Once you solve for x1 and x2, right, those become the operating points for the state variables. And we've designated that as x1 equals x1, 0, which is the operating point, and x2 equals x2, 0, which is an operating point. So these are all the variables, these are all the operating points that you need to have. Specifically, you need to pre-calculate these. After you've done that, then you can determine what the small signal analysis will look like. And so the question that we want to answer is investigate the small signal behavior of the state variables and the output variables in response to a perturbation in the input signals and about an operating point. Okay, so those are all the things that we'll have to consider, but it's a subject basically of the lecture dealing with small signaling analysis, which is going to be lecture 8. So this is again just a summary. State space equations, output equations for this example happen to be nonlinear in just one state variable and one input variable. All right, so just a little bit more in terms of conditions under which a tangential line and tangential plane can exist. We've discussed this when we discussed differentiability, so we'll just revisit the subject. The function, so let's look at the one variable function case and then look at the two variable function case. So in this case, the function y equals f of x must be differentiable at the point of interest if we're going to basically have a tangential line. So the example that you see here, it's clear it's a smooth curve, and so a tangential line exists. In contrast here, you can see there's a cusp at the point top, which means the slope of the curve basically changes abruptly at the cusp, which means at that point, function is not differentiable. Now let's expand the notion of tangent from 1D to 2D. So if we have a curve, it's basically we call a line. If we're dealing with a surface, it's a curved surface. If we're dealing with a tangential line for one variable, then we're talking about a tangential plane for two variables. And this can be extended to higher dimensions. So if we look here, for instance, you have a smooth surface, and you have this tangential plane which just touches at some point on the surface. That's by definition what we mean by tangential plane. On the other hand here, you'll notice it comes to a point. And so if you were to basically try to fit a tangential plane at this top point here, it will not be possible. So this one will not be differentiable, whereas this is differentiable. Okay, so next would be visualization of the tangential plane. So on the left here, basically, this is a 1D, a one variable case. So this is going to be just a linear approximation about this operating point. So even if I were to take this curve and just investigate how it changes, in the limit in this area would be basically a straight line. And this red line is in fact the tangential line to the point at A, f of A. Extending this to two variables where we say a tangent plane is tangent to a curved surface, we'd be looking at the position at this point here, which is AB, f evaluated AB, and the tangential plane basically will be linear in X and A. We'll just touch at this point on the surface. So this is, again, a more of a diagrammatic view in terms of if we looked at a tiny little section at this point on the surface and investigate what the surface features looks like, we can see that it looks curved, but if you make it smaller and smaller, then this approximates that of a flat surface. All right, so there are a number of interactive visualizations of a tangential plane you can look at. This is example one. So you can basically play with which octant you want to look at. You can zoom in. You can look at basically a number of things in this particular example. Second example, there's another one. Here basically, again, you can play with which octants you're interested in. You can even choose a point of operation in the XY plane, right? That is the position that you're interested in at the surface. You can see also there's a blue vector which indicates the normal to the surface. And the red vector would be tangential to a particular curved line. Anyways, you can investigate this in more detail if you wish. All right, so that basically concludes Lecture 7A. Thank you for listening.